All right, so this is our second reach ahead lesson. This one's on something called resonance structures. All right, and it's so hard to teach this unit and not talk about this stuff. And I decided not to with the general class just because there's only so much you can get to, and you kind of have to pick your battles. But this really is one that you want to talk about. So anyway, yesterday we learned that individual atoms within a molecule can have fewer or greater electrons than the valence number. And we're now going to talk about what that implies. The first thing we said is that a structure with no formal charge always wins. So if you remember, we talked about carbon dioxide yesterday, and I want you to see that really there's three ways we could put this together. We could put the carbon making a triple bond to the oxygen on the left, and just a single bond to the oxygen on the right. And we talked about this yesterday, and we said that if you calculate the formal charge, well, we take a quick look and we say, well, this oxygen's only making one bond when it should be making two, so it's going to have a -1 formal charge. And this oxygen is making 3 bonds when it should be making 2, and if you calculate its formal charge, it ends up being +1, one too many bonds. We could also do the middle structure, which is C double bonding to both oxygens. And of course, these will just have 2 lone pairs of electrons like that. All right. And there's no formal charge here because everything is making the expected number of bonds. Carbon is making 4 and both oxygens are making 2. The last thing I want to show is that carbon could bond with the other oxygen by making a triple bond. And this is kind of the one thing we want to talk about today, is that that's not the same thing. You know, we've talked about it like it is, this whole unit, and that's been really tough for me. But this structure on the left and this structure on the right aren't the same thing. They really are 2 different oxygens, even though we kind of say, well, I mean, what difference does it make which one it makes the triple bond with? We're going to talk about today the fact that it does matter. But still, again, this will have a -1 formal charge because it's not making enough bonds. This is going to have a formal charge of +1 because it's making more bonds than it should be. And there we go. Now, remember from yesterday that the structure with no formal charge always wins. So in this case, this structure doesn't happen, this structure doesn't happen, and the one that we actually get is this happy little structure in the middle. And I'm going to show it like, you know, kind of being all radiant and glowing and stuff. Yeah, doesn't he look happy? He's gloating. Not very magnanimous. Anyway, so that's a structure of carbon dioxide, and it is the correct structure. But let's look next at carbonate, CO3 2-, and we're going to draw its Lewis structure. Really quickly, carbon should give us 4 valence electrons. 3 oxygens should give us 18. And the 2- charge should give us 2 more, and that gives us a total charge of 24 electrons. And so when we draw this, I'm going to leave a little room because we're going to end up having to draw a few structures here. So I'm going to draw carbon surrounded by 3 oxygens. We're going to complete the octet of each surrounding oxygen. And when we do that, we're going to count the electrons. And quickly we'll see that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have the right number of electrons. And it's at this point that I'm going to quickly copy this structure. And I'm going to paste it. Oh, geez. What did I just do? And I'm going to move, okay. There we go. I'll give you a chance to draw all 3 of those. But here you see that I did this because really I have a choice to make now. I could make the double bond with the top oxygen, Or I could make it with this oxygen down here on the left. Or I could make it with this oxygen down here on the right. Now, you'll notice that in each of these cases, we end up with a formal charge. So in this case, this has a formal charge of 0 because it's making 2 bonds as we'd expect. But this bottom oxygen here is only making 1 bond. So it's going to have a formal charge of -1. And this oxygen down here is only making 1 bond. And it's going to have a formal charge of -1. Now that makes perfect sense because we know that the whole ion has a charge of -2. So the structure makes sense. We should have 2 atoms that have a formal charge of -1 because we know that the sum of the formal charges has to equal the charge of the whole thing. Likewise here, this is going to give us a formal charge of -1. That'll give us a formal charge of -1. And that works out to an overall charge of -2 for the ion, which again makes perfect sense. And the third one, hopefully not shocking at this point. Again, the oxygens that aren't making the right number of bonds both have formal charges of -1. And that gives us an overall charge of -2. But what I want to show is that all 3 of these structures are really equally valid. One isn't more right than the other because they all have the same formal charge. And if they have the same formal charge, they're equally as likely as one another to actually happen in nature. Right? We said the structure with the lowest formal charge always wins, but what happens when there isn't a formal charge difference between them? Well, then they're all winners. They're all equally valid. And the way we show that actually is with a symbol like this. So we put arrows between them that show that we can go from one structure to the other. They're all real. So until now, you've always been told to just choose one and put the pi bond there. But really, all 3 happen. But it's a little more complex than that because it's not just that only one of them happens and maybe one carbonate ion has the bond on the top and maybe a different one has the bond on the left and a different one has the bond on the right. See, one of the things we didn't talk about in this course is that when you make a pi bond, when you make a double bond, the bond length gets a little shorter, right? And that makes sense because a second bond is going to pull that oxygen a little closer. But when we look at the carbonate ion, no one bond is shorter than the other. In fact, all 3 are a little bit shorter than we'd expect them to be if they were just a single bond. So what we think happens is that we have a resonance structure where each of these makes a partial pi bond. At any given moment, the electrons move in such a way that there's kind of 1/3 of a pi bond happening up here, 1/3 of a pi bond happening down on the left, and 1/3 of a pi bond happening on the right. So another way to show this, and by the way we showed it up top is perfectly reasonable. You're allowed to show all 3 structures and show the resonance arrows that show you that these 3 structures all happen. But you can also draw it like this. I can draw carbon with the oxygen surrounding it. And what I can draw is a single bond and then a dashed pi bond like that. And that dashed pi bond tells me that that's a resonance bond. It's a bond that's only partial. And now when we do it this way, instead of 2 of them having a -1 formal charge and 1 of them not, well, we can say that what each of these has is 2/3 of a double bond. Or, sorry, excuse me, 1/3 of a double bond, 1/3 of a pi bond. And that means that it has 1 1/3 bonds when it should have 2. So now this actually has a formal charge of -2/3. It's 2/3 of a bond away from having the right amount. And this one has a charge of -2/3. It's 2/3 of a bond away from having a full bond complement. And this one's -2/3. And if you look that is equally valid because we said the sum of the formal charges has to equal the total charge of the compound. And in this case, 2/3 plus 2/3 plus 2/3 gives us 2. So since they're all negative, negative 2/3 minus 2/3 minus 2/3 gives us a charge of -2. Now, I don't care which way you show it. You're welcome to show all three structures like we did above, or you're welcome to show the one structure with the resonance bond there. And I quickly just want to cover a couple points on the next page. So the first thing to understand is that when we make resonance structures, the only thing that moves is pi bonds. All right? We still have to form a sigma bond between everything, and we still have to obey all the rules of making a Lewis structure. Every resonance structure is a valid structure, right? If you look at each one of these three, everything involved has a stable octet. There's a sigma bond between everything. All of the rules of a Lewis structure are obeyed. So you can't have some structure. You know, I couldn't choose to make one of the resonance structures just carbon bound to oxygen, bound to oxygen, bound to oxygen, like this. That's not a valid structure because carbon doesn't have a stable octet. Right? So that wouldn't be allowed. You can't make a resonance structure involve something that has a formal charge of greater than 1. So you couldn't have a formal charge of 2 or 3 on anything. If it's not a valid Lewis structure, it can't be a valid resonance structure. It has to be something that can really happen. All right? And so the formal charge of a Lewis structure is fractional. And I've already showed that up here, which shows that I was getting ahead of myself, right? But that's okay. We'll show it one more time. And we'll say carbon is bonding with oxygen. And then in each case, it has 1/3 of a double bond. And so if we wanted to calculate it a little differently, we could do it this way. We could say the formal charge of oxygen is going to be 6 minus you know what? I'm going to change my mind and just say that the way to do it is just by the eyeball method. I don't want to complicate it by having to draw the electrons in this case. So we're not going to worry about that actually, and rather we're just going to say that the formal charge of oxygen, because it's making 1 1/3 bonds, all right, the full bond of the sigma bond, and then because that pi bond is divided evenly between the 3, that's 1/3 of a bond, because it's making 1 1/3, not 2, it has a formal charge of -2/3, -2/3, and -2/3. All right, but how can we calculate that easily? Well, if we take the average formal charge for each bond, that tells us the formal charge of the resonance bonds in the single resonance structure. So if you actually wanted to sit down and calculate by hand, you actually would have to draw all 3 structures out. All right, like this. You'd have to draw the first one there with 2 electrons. All right, and these with 3 pairs. And then you'd have to show that this resonates with a second structure where the single bond is up here and the double bond goes down to the left, because that's an equally valid structure. And then you'd have to show that that has resonance with this third structure, where this is a single bond again. This one's a single bond this time. And now the double bond is on the right. Those are the 3 valid resonance structures for this. And what you would do to calculate to calculate this, if you're not just eyeballing it, and you can just eyeball it, the way we actually work it out for sure is we could look at the top oxygen, this one here, and here we would say it's 6 minus 2 bonds minus 4 electrons equals 0. So here this has a formal charge of 0. Here, though, it would be 6 minus 1 bond minus 6 electrons for a formal charge of -1. And here it would be the same. It would be 6 minus 1 minus 6 equals -1. So we would put that there, and we would say the top oxygen has a formal charge of 0 minus 1 minus 1 divided by 3. It's just the average, and that works out to -2/3. And we could repeat this process for all 3 of the oxygens. We're going to get the exact same number. We could also repeat that process for the carbon, but of course in its case it's 0, 0, and 0. So that's just going to work out to 0. All right, and so you can see that if you want to, you can calculate the formal charge. The long form, it just involves figuring out the formal charge of each atom on each and every resonance structure, and then taking the average. This particular compound only has the 3 resonance structures. Some have more than that, some have fewer than that, but the concept holds. There'll be some homework attached here. I haven't attached it yet, but it'll be forthcoming. So I hope this made sense. If you have any questions, don't hesitate to ask for help. Have a good one.